toss the coin n times and observe the heads. Let's say k naught heads are observed. So this is some new information. So the question is how to update our knowledge about FPP. And this is where this conditional distribution is. So conditioned on what? Conditioned on some new information. That's the whole point. Here. All right, so you can argue that P could be, it's a coin, it could be 0.499, 0.501, 0.49, 0.5. It doesn't, so it doesn't have to be certainly discrete values of 0.1 point. So that you agree, it doesn't have to be discrete. It could be anywhere, but you may say, look, it's more like, so that's only a matter of taste. It's more like this possibly, maybe, but you can certainly see that any value between 0 and 1 are acceptable, isn't it, for small p? In other words, this is, I'm not asking you to confuse with the discrete probabilities of getting k heads in n tosses. Those are discrete numbers. Here it's a coin. The probability, the coin represents by its construction biased or unbiased, right? Most of the coins are, let's say, unbiased. But if it is biased, the probability of, this is just the probability of getting a head. It could be, it is usually some value around 0.5. But to make it simple, I could say it is like this. It is certainly, you agree, it is certainly not like this, because why are you excluding? This is again making prejudiced assumptions. Why am I excluding all these values? So it's certainly not discrete, right? It's continuous, but I agree with you, it's most likely it is some shape like this, but I don't know this shape. And so to start with, very beginning, if I'm given a coin, I'm going to assume that all values are possible. This is essentially saying all values for P are equally likely. Yes or no? What else can you conclude if you have no other information? All right, so again we go back to our, to make progress here, I go back to conditional probability. If you recall, we wrote this as PAB over PB. And not we wrote, this definition makes sense because it obeys all axioms of probability. So I'm going to replace here in this definition, suppose I replace this by x less than x to bring in the random variable. So this now reads probability of x less than x given b. And this of course is now using the x less than x, this event intersection with the b over PB. But if you recall, the distribution function is of course probability of x less than or equal to x. And the density function is the derivative of that with respect to x. Both are non-negative, this is non-decreasing, etc. So using this, we could write this if you want as the conditional distribution function of x given b, because using this notation. So this is the unconditional distribution, unconditional density function. And taking the q from here, we could write like this. And of course, if you have the conditional distribution, so this is the conditional probability distribution function given b. B is some event. So I'll come to this problem. This is what we want to address. This is a practical problem, but let me develop some little bit theory. And of course, if you have any density, any distribution function, you take the derivative. That gives you the conditional density function. And again, we can quickly check that all the properties are true. You put x equal to minus infinity, this will be the null set, so this will be 0. If you put x equal to plus infinity, this will be the whole set, pb over pb is 1. And similarly, you can prove that the monotonic, non-decreasing nature, etc. So we'll denote this by like this. So this is the conditional PDF, probability density function. And it's the other way also it goes. In other words, from here, the integral of this it gives you the distribution function. So let me, before I do that problem, you have to do it a bit more. Let me do an example. Suppose B is given to be, this is an example. Let's say x greater than a. This is given to us. This is the observation. So question is, how do you modify this in presence of this observation? This has happened. The random variable is known to take values only beyond a. So we'll use this definition. So we will start with the distribution function. I'm going to, so we'll draw it below this so that you can get it. So you have A here, and we want to find out the conditional distribution. So remember, if you look here, something happens at A. So we should do two cases of interest, x less than A and x greater than A. So I'll do it for x less than A and x greater than A. So the definition is here. I'm going to, so this is probability of x less than or equal to x intersection with b. B is x greater than a divided by probability of x less than or equal to x intersection with x greater than a, that's b, whole thing divided by probability of x greater than a. So there are two cases, x less than a, x greater than a. So let's do one case, x less than a. So a is here, A is here. Let's say x is, small x is less than a, so small x is somewhere here. So we take the intersection of these two sets. One is x, the random variable capital X falls in this region. That's what this is. The random variable X is occurs less than, here it says the random variable occurs beyond A, so that's here. So what's the intersection of these two? Null set. So in this case, this is, we are doing this case, so this is 0. The numerator is 0, so the denominator is 0. So let's do the other way, the other case. So once again, A is here, but in this case, X is beyond that. So once again, X less than equal to A, so the random variable is somewhere, anywhere here. And this is the event where X is greater than A. X is given to be greater than A. So their intersection gives you, X is between A and X. So the numerator is the same as A and X divided by, so this of course you know you can write it this way if you want. So I'll rewrite from last week or 2 weeks back. This you can rewrite in terms of the distribution function or density. What is it in terms of the distribution function? Anybody? This is for small x less than a, small x greater than a. And it's a derivative with respect to x gives the density function. Derivative of 0 is 0. Derivative here, this is a constant, this is a constant. Derivative of this with respect to x gives us what? Small x, small f, right? So that's going to be fxx. All right, so if you check the another example, so I'm just going to copy it here. So the density function is simply a scaled version of this for x. What is this? This is this is x greater than a, and this is x less than a. So this is a scaled version of this, right? Except it is. Remember, the denominator is greater than 1 because this is a probability. So it will get scaled up. And the distribution function is 0 up to here. So it's 0 up to here. And then when x equal to a, you can see here it's still 0, right? X equal to a, the numerator is 0. So then it goes up. And scales and shifted, so it sort of goes up. And what's the value at infinity? 1 minus this divided by this, so that's 1. So everything checks up. Let's see whether area under this. Area under this density function is this only valid from a to infinity. That is 1 minus fx of a, which is the same as this, cancels and you get 1. So area under this is also 1. So you could expect problems like this in the. So check out the other videos. There are 2 other examples. So let me move on and make a connection to this. Okay. Any questions before I?
Does all these conditional function will only
Here it is changing, right? Here it's. I mean, it's not going to at least. See, here it is shifting and scaling.
Shifting.
No, it is subtracting something. So subtraction will definitely change the tone, right? But if you're asking, will it square? That's not going to happen. It's a linear shift, right? At least for these examples. You have an issue here? You have figured out? What is the question?
I don't understand why the integrate of the
Last one. All right, see, let's integrate this. So integral of fx of x given b dx. What are the limits? So that's going to be 1 over 1 minus fxa is outside. A to infinity fxx dx. So for the ordinary density function, how do you express this in terms of anybody? 1 minus the integral from minus infinity to a fxx, right? But this is fx of a. 1 minus fxa over 1 minus fxa is 1. All right, so let me try to get to the problem that we started. So to make further progress, let me bring in another identity that we have gone over. Say we want to compute the probability of B given. So things like this. Remember, after all, this is an event. So I can certainly write this as probability of x greater than x1 less than or equal to x2, AB intersection B over PB. Now, anybody remembers how to write the numerator in terms of the distribution function? If you don't remember, let me quickly redo this. So let's say x1 is here, x2 is here. So x2 is greater than x1. So we can write x less than, this event, x less than x2 as the disjoint union of union. Right? This is no big deal. The x less than x2 is here. That's x less than x1 plus x between x1 and x2. So these two are mutually exclusive. So of course, probability of this is probability of this plus probability of this. So from here you get, this is the distribution function of x2 is fx of x1. So we had this a while ago. So this probability is the difference of this distribution functions. Let me do an intersection with the B here, just to bring. So that will be, remember, this is like logical addition. So B here, B here. And this is the problem. So again, these two are mutually exclusive. So from here you get probability of x less than x2 and B is probability of x less than x1 and B plus probability of x between x1 and x2 and B. So this is the probability we want to compute. So I can write this as probability of, but of course, this is, we have gone over this before, right? This is this divided by PB is this divided by PB plus this divided by P. And this is the term we are looking for there. And this is, of course, we can write this as probability. If you call this to be A, probability of AB given B is A given B. So this is x less than x2 A given B. That's the distribution, conditional distribution function equal to probability of x less than x1 given B plus probability of x being between x1 and x2 given B. So this is fx x2 given B minus fx x1 given B over, that's it, right? But this also I can write it as we had the, yeah, it's here, from here. now consider x1 to be, bring these 2 points to very close together. So x equal to, x1 equal to x, and x2 is next to it. Let's say x plus delta x. So this right side now reads, just epsilon positive. So these 2 points being very close, this integral is just the value at 1 point multiplied by epsilon. So we get this identity. And on the other side, this, if you want, also you get this one. This also be, so on the other hand, this we can also write it as b given x between x1, x and x plus delta x. I'm just using Bayes' theorem, right? So this is, remember, if you read this as A given B is B given A, this is A, multiplied by PA divided by PB. But we have already computed this, so I'm going to substitute this on this side. This is fx of x given B multiplied by epsilon. Now, how do I simplify this? And this term itself is what? Integral from x to x plus delta x fx u du. So this term, the last term is going to be fxx multiplied by epsilon, not delta x, epsilon. Again, by the same argument, this integral can be approximated. So that's this term. And the denominator is just a pb. And in the limit as epsilon goes to 0, this now reads. So the whole idea is that we consider this and then let the epsilon go to 0. So we'll consider that limit in a. So now if you consider, before I fill it up, so this is still with the delta x equal to epsilon. Now let epsilon, so notice that this is an identity and I can cancel an epsilon here and an epsilon here. That is still good. So the left side and right side are good. Then now if you push the epsilon to 0 towards, to take the limit, this side and this side will equal and we get this identity. So I'm just going to start with that. That's all we need here. So this, I use this symbol, I hope you sort of followed my logic. So I have this result. For any event B, this is true. So PB multiplied by this from here, PB multiplied by that equal to so we are going to use this to update our knowledge about X. So remember the story, you have the unconditional density function. We have fxx is given, then B occurs. The question is, how do you get this? Right? So I went through a couple of examples. We already know the definition of this. This comes from the distribution, derivative of the distribution function. Depending on B, I did a couple of examples. And this is also true. If this is true, I can integrate on both the sides from minus infinity to plus infinity. So you get PB multiplied by, because PB is a constant. So you get this expression. What's the value of this integral? Anybody? Area under any conditional density function. Right, that's a density function, that's one. So we get, right now it looks like a bunch of formulas, but I'm going to show you its usefulness. So we get this formula. So we get that one, and finally I'm going to substitute that into this expression. So I'm going to go here and write so this is this divided by PB. PB I'm going to plug it in from here. So the question is, how do you update it? So we have the answer here. So how do you update these two is fx of x given b. You learned something. You use this experience to update your previous position. So that's going to be, so of course the experiment becomes important. Pb given x equal to x. So you can see this is sort of a generalized version of, again, it's all from base. So more on inference of it. All right, so the question was, how do you update your knowledge? The answer is here. You start with something, maybe common sense, or otherwise you make some general conclusions. And then you perform an experiment. So the new data comes in here, data. So you have to respect the data. How do you use this data to update your knowledge? So we are going to use this to solve this problem. And then we can make predictions. So what is the probability of getting ahead in the next toss? So how do you answer this, etc.? So I'll try to answer this using this framework. So quickly, let's go through this, the problem that we have posed. So remember, this is sort of a lot of manipulations. Now you're going to see how to use this to solve a problem. So this is a real problem, right? As I said, a coin is given to us. We have no idea. So you assume that P could be anywhere. So that's the same as saying this. But then you can, of course, since the coin is in your can, it is up to you. You can toss the coin and see what happens. So you tossed it 100 times, you got, let's say, 59 times heads. So that's a fact. Question is, how do you use this to update this? So let me do that here. Any questions? So the experiment there is a sequence of heads and tails because you are just doing it. Remember, you are not considering all the outcomes. You are tossing n times and you get a sequence. So A would look like this. So if you start counting the heads, 1, 2, 3, etc., it says we have k naught heads. And the total experiment, if you start adding, we performed in the experiment. So that's the A. This is the event A. And we know that these tosses are independent. So probability of getting A for a particular value of P. So if you assume that the P is somewhere here. Instead of capital P, in order to confuse, I'm just going to call the random variable to be X. Too many P's. This is capital P. So P could be, for a particular value of P, this is going to be P, this is going to be 1 minus P, P, etc. So that's going to be P to the power Q naught, 1 minus P to the power N minus K naught. I'm going to write it as so now we can use this expression to find out PA. So PA is integral PA given remember ultimately this you just need to A is B here. We have this one. This is uniform, so we just need to find this. So if you want to rewrite for our experiment, so this is new data on experiment. Some event of interest was corrected with X. So how do you update the information? So this is A given X equal to P multiplied by FPP, Fx.